Thank you, everyone. My name is Matt DeBergalis. It's great to be here, and thanks for taking the time to learn more about JavaScript and HTML5 over the course of the next few days. I'm one of the co-founders of the Meteor project. We're a team of about 30 people here in San Francisco and around the world working on a full-stack JavaScript application platform, which means you can write a complete app for web, for mobile, and down the road for thermostats and IoT and all the other places that people expect an app to run, with a modern interface, something that feels great in 2015, in pure JavaScript. So with Meteor, your code base covers the whole thing, the code that runs in the browser and the mobile device, but also the code that runs in the cloud that implements your trusted business logic or your application-specific logic that integrates with first-party or third-party microservices. It's used all over the place. We have thousands of companies using it in various ways. Here's an example I like of an app built for Honeywell to help size industrial tanks, which turns out to be a real thing. And it's a good example of what people expect, I think, in a modern application today. It's got to run on both the phone and the desktop. And it's not just shrinking the app that's on the desktop down to the phone. This is a different experience depending on the kind of device you're on. And if you look at the case study that OpenRoad, a partner of ours, wrote about this, they talk about what it means to be building a modern app like this in 2015. So I don't want to talk too much about Meteor today. What I really want to do is talk about a new architecture for building applications in JavaScript. It's something we call connected client. And the need for new architecture is a big reason we built Meteor, but that's just one example. You'll see this architecture in all kinds of new apps, some of the things that we're most fond of on our phone or inside our browser. And I suspect many of you will recognize parts of what I talk about in the apps that you're building today. What I really want to do today is convince you that thinking about these apps as a new kind of architecture, in many ways a departure from the web architecture that probably most of us grew up with and learned software development in, can be a helpful way of rethinking the essential parts of how you structure the app and gives you a path forward to writing that app more quickly, with a more agile team, and with a better result. So to do that, let's start with that shift that I just alluded to from an era that we might call the web era, the website era, to the current era we're entering of apps. It's a big shift in the industry. And the big driver, of course, is mobile. Now that we all have a supercomputer in our pocket, now that we have a computer in our car, in a thermostat, really everywhere, it drives a desire for a new kind of interface, a new kind of user experience that wasn't possible in an era of websites. And so I have some examples of this. Right on the left, we have a classic example, the premier example, arguably, of the beginning of the web era. And on the right, we have some examples of newer apps. Facebook and Uber, I think, are two good ones. The interesting thing for me isn't just the fact that you can use them on your phone, or frankly, that most people use them mostly on the phone, but that it's just a completely different kind of user experience. Right? When we think about Uber, the whole thing would fall apart if you were thinking of it as a set of web pages. Right? You need to be able to see the cars moving around. The drivers need to see you in real time. Or even Facebook. It's not just Messenger, it's not just chat or the live feed of events on the side of the screen. It's also, it feels a bit like a desktop app, right? It's got dialog boxes, autocomplete, modals. It feels actually a lot more like the software we used to use in some ways on Windows 15 years ago than it does what a classic web application might look like. So behind that, it turns out there are some big architectural differences between the web era of the past 15 years and the new era of apps. The web was stateless, right? The web was built around a protocol that was specifically designed to be stateless request response, HTTP, which meant that every request coming from every client was independent of any other client, any other request. Apps aren't like that. Apps are stateful. They remember things. They keep track of what data is inside the client. The very fact that we're running code on the edge of the network is a big reason for this, but there's actually a lot behind it that I'll get into. And because of that, we have to move from a request response model where the client is initiating every transaction, every transfer of data, to a pub-sub model, where the server can push information into clients just as easily as clients can ask the server to do something on their behalf. That turns out to be a fundamentally different direction of application architecture. Another big difference is what's on the network. In the web era, traditionally, the network was about documents. And we've come a long way. REST doesn't tell us that we have to put an HTML document on the wire, right? It could just as easily be JSON. But a lot of the heritage behind HTTP, behind the whole infrastructure that's built behind that, the verbs that we have in REST, it really does come from a heritage of transferring a hypertext document from one end of the network to the other. And it turns out that in these modern apps, it's not presentation at all that's on the wire, it's data. So whether that's being pushed from the server or whether the client is asking the server for something in particular or sending in a request, these are all semantic messages that are typically structured JSON or some other format where the information on the network is actually structured as data. And the reason behind a lot of this is that in a modern app, whether we're in the browser or on mobile, when you think about it, the app doesn't reset every time I do something. So in the web era, I'd click a link, and I'd wait a couple seconds, and I'd get a new page. Or I'd fill out a form, and the beach ball would spin for a minute, and then I get my form submit result. But when I build for mobile, that interaction pattern isn't right at all. So there's a much more responsive, there's a much more engaging kind of response. And because I'm not redrawing the whole screen every time I tap on something in mobile, I have to have a way to keep my data up to date on the screen without going through this whole process of requesting one document, be it HTML or JSON, at a time. And so we moved to this more fluid model where the data is flowing in both directions. So the architecture for these apps, and this is the point I want to make here, is really different. And the teams and the groups that are building using this new kind of architectural style can actually move much faster. And it shouldn't shock us that it's such a big change, because it's not the first time this has happened in the industry. We can look all the way back to the 70s when software ran on mainframes in big data centers, right? You connected to it with a terminal, an actual terminal, right? VT100 or 3270. And that was great until sometime in the mid-'80s, Intel figured out how to make a cheap microprocessor. And all of a sudden, for the first time, it was possible to run software next to the person using it in the form of a PC. And in really just a few years, the way we wrote typical software, not that mainframes went away, but the way that we wrote typical software changed dramatically. And it gave us the rise of Microsoft and Windows and the Win32 APIs, transaction processing, middleware, application servers, a whole set of technologies that sat underneath the software that was completely different from what we used in the mainframe era that preceded it. And then again, around 2000, what happens? Well, the network, the internet, becomes pervasive enough that we can actually deliver an application as a URL. And the advantages of that, the distribution advantages of being able to tell someone to go to your website, instead of having them, I don't know, pull out a CD from Best Buy and install it in their computer, were so dramatic that, again, over the course of a few years, we shifted the whole way we wrote software. And the languages, the technologies that were core to the Win32 era, the technologies that every developer knew about, essentially gave way to a whole new set. We use different languages to build websites. I mean, ask Borland how that transition went, right? We use different technologies for drawing the screen, different protocols on the network. Very little, in fact, of what was dominant in the Win32 development cycle carried over into the web. So the same thing's happening here with connected client. We should expect to see as dramatic a change as we did in the year 2000 with the rise of Salesforce and Amazon and these other software platforms that were built around the web, as we are going to experience now with the move to mobile. So what's behind this kind of application? What is a connected client app? Why do we care about this? Well, I think there's a few things that we can really hold on to as architectural underpinnings for the best built apps like this. So I've talked about stateful. Let's dig into that for a moment. There's a couple of reasons that these apps are stateful. One of them is because we want this really interactive experience, particularly on mobile. It turns out we can't afford the cost of a round trip to the server, to the cloud, every time the user does something in the app, right? I mean, think about the experience of using an application on your phone. If you paid the 500 milliseconds that it takes over 3G to go from one part to the next when you made a swipe or scrolled into another part or went into a detail, the app wouldn't feel very good. So it turns out that unlike the web era, when we can build everything around a single request and be very chatty with the database, think about Rails and Active Record and that whole architecture, it turns out we have to cache information on the client if we want any kind of reasonable experience for the user. And once we have a cache on the client, we have a distributed cache because we probably have thousands or millions of clients. And all of a sudden, we have a very stateful architecture, very, very different. Because once there's data cached on the client, that must mean that the server, the cloud, is keeping track of all those clients. Because that's how the cloud can keep those caches up to date. Remember, the screens have to update on their own as information changes. Or at the very least, the application, as you move from part to part, can't show you stale data because you didn't happen to hit the refresh button that doesn't exist in your mobile app, right? So the server is keeping track of every client and exactly what data is being cached on that client. The network is stateful because now we've got a WebSocket, or maybe we're faking it with XHRs, but fundamentally we have a stateful network connection between the two because, again, the server's constantly pushing new information to the app. And this is true no matter what language you build this stuff in. It's true no matter how you architect it. You're going to find if you inspect the guts of those apps, there's constantly this data flowing back and forth. And if you look inside SoundCloud or Facebook or Uber, any of these modern applications, you'll find this kind of stateful caching architecture in one form or another. Here's another example of stateful. We've got code on both sides of the wire. So we don't just have code running in a homogeneous environment in the cloud. That was easy. That was the web era. It was the classic, horizontally scaled architecture, and I'll talk more about that in a bit. We've got code running on devices, lots of different kinds of devices probably. And so when I do a version update, when I want to do continuous deployment in a connected client app, I need a story for how the cloud is going to securely push a code update into the device, into lots of different kinds of devices. And again, that requires that the cloud be keeping track of all those connected devices. Who's actually out there, right? And what version are they running? And when is an appropriate time to disconnect the WebSocket, restart the client running a new version, and then reestablish the state that I previously had? So from client to server across the network for lots of different reasons, we have a stateful architecture. And I can't stress how different that is from the web era that we're all used to, which was all about building stateless, horizontally scalable, share-nothing architectures, right? We're just not going to get very far if we continue down that path, building a connected client app. OK, another big hallmark is reactivity. You just heard a talk about React, and I'll talk about this in a little bit as well. But because there's no refresh button, it turns out the way you want to build these apps throughout your stack is reactively. In other words, each part of the stack should react to changing data, changing circumstances, and should automatically, in a declarative way, update its responsibility based on that changing information. And finally, as I mentioned, we've got code on both sides of the wire. So the application itself, in some sense, spans the network. Very, very different from the web era where we thought about applications as being completely contained within a server process, my Rails process or my Java process, right? And in fact, I think what you just heard at the end of the previous talk is really germane to this point. Here's a more nuanced way to look at a modern connected client app. Think about the app, everything we've been talking about, right? The parts that run in the cloud, the parts that run in the client as one thing. And it's separate from the microservices. So I'm not talking about your internal service for billing or application data. I'm not talking about maybe your third-party microservice for geo. But the app itself, the part that drives the user interface, the part that determines who can see what data, when to push new data to the client, all the policies that go into the app. That stuff, in the most sophisticated companies, is owned by one team. That's because it can be one team's responsibility to roll out a feature across all the different platforms that you want to use. It's much more agile to develop a connected client app when you don't have to break apart the backend team from the iOS team, from the Android team, exactly what you heard before. And if you look inside Facebook, Twitter, Asana, lots of companies, Meteor as an open source example, the most agile teams are making the fastest progress precisely because they can bring one team of developers to that entire app instead of having to have separate specialists with different libraries and technologies and languages that can't very easily move from one part to another. So we're still learning a lot about this architecture, but we do know quite a bit. And what I wanted to do is spend a little bit of time just talking through some of the hallmarks of this, some of what we've learned so far, and some of the interesting directions that I see coming over the next, say, year or two. So here's the first one. And I don't think this will be a shock to people here, maybe more of a rallying cry because we're right. JavaScript's the answer. And it's the answer for a very specific reason. It's the one special language that actually runs in all of the places that your app has to run. Think about it, right? It runs in the cloud. That's Node. It runs in the browser, of course. It runs in mobile. That's well, frankly, massive investments on the part of Apple and Google, but technologies like Cordova and Crosswalk and so forth are a big part of that story. It runs on Raspberry Pi. It runs on probably Hitachi SH4s or whatever they're using these days. It's grown into the most pervasive, well-known, and well-performing dynamic runtime that we've got, right? And no other language can make that claim. You can attempt to build a cross-platform app using Java or some other language and cross-compile to all the different targets, but it turns out in 2015, there's nothing better than pure JavaScript for building these things because it's been, it's had so much investment by so many companies and so many developers now that the momentum is impossible to stop. And it's getting a lot better. So how many people remember this book? Right? It's pretty thin, as I recall. It was a good half-hour read. There are a lot more good parts. So I want to show an example. I'm borrowing this from one of the fellows on the Meteor core team, Ben Newman, who gave a talk at Meteor Dev Shop a couple months ago about our recent transition to ES 2015. So there's a new version of JavaScript, ES 2015. I guess it's, what, 2,010 versions better than the previous ES5. It's actually really good. So for the first time, we have classes, we have modules, we have all the little nitty-bitty stuff, a lot of which Coffee tried to address, now standardized as part of the language. And it's made life a lot better. So at Meteor, we've completely invested in ES 2015. It's the flagship feature of our latest Meteor open source release. And we've written our own, or rewritten, I should say, a lot of our own code in ES 2015 style. I won't go through each step of this, but I want to give you a taste of how much better and more concise and agile the new language can be. So on the left, we have actual code from the Meteor tool, the command line build tool, written in original ES5 style. You'll recognize this stuff. It's like classic. How do I make basically like a class hierarchy in ES5? And so I've got a basic function that serves as a class constructor and a prototype chain, and I've got one method here. On the right, we have the equivalent in ES 2015. And actually, the first nice point is that that is valid ES 2015. So you can make this transition gradually. You don't have to rewrite your whole app in one shot. But watch what we can do. ES 2015 has classes. So I can get rid of all that weird prototype chain stuff, and I can replace it with a very normal-looking class definition. Think about how much easier this is to learn. Think back to how long it took you to figure out what a prototype really was and how to really use it, and that your team had to agree on how you were going to use it, of all things. Now we have basic classes. In fact, we don't even need a constructor in an ES 2015 class if you're just going to call the super constructor. So we can get rid of all that stuff. We've moved our method into the class definition. That looks a lot better. We can go further because it turns out that ES 2015 has a way of passing a structured set of options as an object that are named into a function. So we can have this destructured data source map path set of arguments instead of all these weird options arguments that weren't self-documenting in the code. And finally, this whole business around exporting our class, well, that's now moved into the language itself, which has native support for modules. So this is literally the transition we made in this particular file from the original ES5, which you can finally get comfortable with, into a modern language that supports the kind of stuff you need when you're writing a very large app. So we couldn't be more excited about this, but it does raise some questions. what are the right set of ES 2015 features to use? Because there's a lot. And how do you know that they're supported on all the devices you might want to run your application? Because this doesn't support ES 2015 natively. So there's still a process where you have to transfer ES 2015 code into equivalent ECMAScript 5 code. So how do you decide which features you'll support and how you'll make that transition? How do you set up the toolchain for that? And I think most importantly, how do you actually use this stuff in a large app? So how do I structure my classes in an app? Should I have one class per file? Should I have those classes be part of an individual component, or should they somehow reference a different part of the app? What are the connections between the different classes? Think about writing software for the web era in a technology like Spring or Rails. There are answers to these questions. But in JavaScript, we don't have those answers yet because there's no agreed upon standard for it. So we're making progress. Certainly at the low level, I think there's been some great work around showing developers the best way to use these new features. This is the Airbnb JavaScript style guide, which I'm quite fond of and our team likes. And we can go further. This is a document we're starting to write at Meteor around how to think more high level about structuring your application using these kinds of ES 2015 features. So ES 2015 is a big deal. I would encourage you, I'm assuming you're going to use JavaScript, I would encourage you to use the latest version. You'll find it's a much more productive environment. And once you've made the transfer, it just seems a little silly to go back. Here's another architectural topic, reactivity. We've been hearing a lot about this over the last couple of years. I think it's now entering the mainstream of development around how you want to structure your application. I want to talk about full stack reactivity. So we think a lot about reactivity in terms of the view layer, right? With technologies like Angular and React, Angular 2.0 in particular. That's great. It's really helpful to not have to think about how to make the DOM do what you want. The DOM is an old web technology. We're not quite ready to get rid of it, though we're working on it. But you don't want to use it in an imperative way. And if you think about all of the code you used to have to write if you built your app in jQuery or Backbone, it's so much better to switch to a model where you can declare what the template or the component should look like based on some input data and not sweat the details of how you move the screen from one state to another. But you really want that reactivity to go further through the stack. So what I have up here is a basic architectural diagram of the Meteor version of this. And let's actually start at the bottom of the stack with the database in the cloud. So in Meteor, and I think you'll find the equivalent in a lot of apps that are built this way, database queries are live updating. What that means is that when you do a database query on the server, what you actually get back is a handle that calls you back as the results of that query change. Because when you think about it, a reactive app, think about building a messaging app, or think about what it would take to keep your to-do list in sync across multiple users. Fundamentally, the database needs to tell you when some information changed. That lets you build decoupled applications where different systems are all making writes into the database at the same time. And you can implement that in a lot of different ways. We have a technology that actually watches the MongoDB replication log to do this in a scalable, high-performance way. But you can approach this in a lot of directions. What you want, though, one way or another, is you want a way to be notified of changes in your data store so that those can propagate reactively up through the rest of your stack. That also means you probably want a WebSocket, right? Because that means the server just found out about a change from the database. Well, what's it going to do? It's going to push that change to some set of clients, right? Presumably, a database change means some set of clients using your to-do app are going to get notification that someone finished a task. Or in the Uber example, some set of clients within a mile of the particular requesting user are going to see new locations of new cars. So we're going to push that data over a WebSocket. If we can't use a WebSocket, we can fake that with XHRs or other techniques. And then we get to this cache I've been talking about. So where does the data go? We want to cache it in the client. And so what we've built is a reactive cache, which means, first of all, it stores the data that's coming over the WebSocket. And second, when you query against that cache, the queries are again reactive. In other words, anything that depends on the results of a client-side query, a query that only hits the cache, also update as the data changes. So that reactivity continues to propagate up through the stack. And finally, of course, there's the view layer. So we can bind those queries into setting the state of a React component or into helper functions that are called from a Meteor template. And when those dependencies change, when a database query changes, which is pushed over a WebSocket, which is stored into the client-side cache, which then invalidates the particular data context of a component, your screen updates. So when you glue all those things together, you end up with a very nice, consistent, easy-to-develop environment. So in Meteor, for example, rather than writing REST endpoints, where it's a static request for a piece of data, we actually write publications. It looks the same. Here's an example publication that returns a set of tasks that are either not private or owned by the user asking for them. In other words, show me all the public tasks plus my task. And on a client, we can subscribe to that, which establishes a request to the server to continue to keep those items up to date. It gets more nuanced than that. Something that almost any application needs, it turns out, is not just a reactive stack from the bottom up, but an optimistic UI. In other words, a way to update the local screen as a user interacts with the app without waiting for that round trip to the server I talked about. So for example, in this diagram, at the top we have our view layer. So this is our actual component, whether it's React or Angular or Blaze. That component needs to redraw. If I, for example, click a button, if I don't know, post a message, let's say I'm building something like Slack on the phone, I can't wait for that network latency to go all the way back to the server to write to my database, only to then have the server push the fact that I wrote a message. I know I wrote a message, I just wrote it, right? So there needs to be a shortcut, some kind of optimistic attempt to directly update my screen on the client. And the obvious way to do this, what we did in the jQuery or the Backbone era, was to write some extra code, right? So there was like local IDs you may remember, or a way to fake the local collection as you made a change, and then somehow resolve that once the server actually completed the request. It turns out there's a way to structure all that inside the framework. It's not different from app to app. And so in Meteor and other systems like it, you can actually do what we call a method call, an RPC, and the implementation of that RPC lives on both sides of the wire. So yes, we're going to go to the server, and we're going to make a change to the database running through all of the business logic and the authentication and authorization checks, but we're also going to temporarily optimistically update our cache. That's going to immediately update our screen. It gives us a very nice responsive interface. And then we have a way to resolve in the event that there's a difference between what we optimistically attempted to do and what the server ultimately did. There's a predictable way to resolve those states back together so that we have a consistent view on the screen. If you take that picture and you rotate it 90 degrees to the right, you get the diagram from Relay. So Facebook, in their open source project Relay, is thinking along exactly the same terms. So we have a server. They use GraphQL, which is a technology that we're very interested in. It's a nice way to structure how a client is going to ask a server for data like we've been talking about, push it into a store, a cache on the client. That's going to drive components by setting their state, and actions on the client optimistically update the cache, but of course have to go to the server to determine their final value. So the trend of pushing reactivity further down the stack, I think, is a very important one, and the technologies that are available are starting to mature and give people a way to do that in a way that doesn't tie in too much to the specific app you're building. Let's talk about another big trend, which is containers and DevOps. So there's some big differences between the way we want to do DevOps and network management in a connected client app, and the name kind of gives it away. These clients are connected. So very, very different from what you might want with a classic Rails app that's stateless. We're going to have to build different DevOps to manage the fact that these clients are connected and they have state. So this is a block diagram of Galaxy, which is a cloud runtime we just announced at Meteor, which is designed for running connected client apps in the cloud. It kind of looks like a normal thing you would build on top of AWS services, for example. We have an ELB, and there are connections that come through, and they get routed into an appropriate application backend. But there's actually some important differences. For example, Galaxy uses what we call stable sessions. So here I have a diagram of a client that's connected into a particular backend for app A in my environment. So it routes through a proxy tier and then into the particular application. What happens if I drop the connection? Let's say I drive through a tunnel and my WebSocket gets disconnected. Well, it's actually very important that that new connection, when the client reconnects, be routed to the same backend. You don't want to randomly route between backends because the state of that particular client is held on that particular backend. And so we have something called stable sessions, which is a way for the internal proxy layer to ensure that that WebSocket or a set of XHRs, if you're simulating a WebSocket, are always consistently routed to a backend. But you have to go even further. Suppose that the actual backend process dies, and with it, the state of your client that was connected to it. Well, so now we need to find a new backend for it, and that becomes the new stable backend. So the behavior you want out of your proxy layer in a connected client app is actually quite different. It should try very hard to preserve the connection to a particular backend. But once that's not possible, it needs to establish a new backend as the primary backend, as the backend for the client, and then maintain a stateful connection to that. Very different from what you'll find in your typical shared nothing, horizontally scalable, turnkey architecture for running web apps in the cloud that are all built around the idea that you can randomly route these requests wherever you want. So Galaxy is built as a layer of connected client management technology on top of traditional infrastructure. And in particular, we run on top of the AWS infrastructure, so everybody knows and loves that. And we run the application processes inside containers. So I think everybody's been hearing more and more about Docker and about containerization as a lightweight technology for letting us run lots of copies of basically the same thing inside our infrastructure. It's great. We're big fans of it, but we need to go further and talk about orchestration, which is the next generation of how to use containers at large scale. So think about what it takes to manage thousands or even millions of application containers. Well, it turns out you want a reactive architecture. And the leading technologies in container orchestration are themselves reactive. They're declarative. In other words, I don't attempt to describe exactly what back-end machines each container is going to run on. Instead, I define a policy, right? A set of rules that explain things like, if I have an application and I want it to be highly available, I need to spread its containers across virtual machines that themselves are in different availability zones. On the other hand, I need availability zones to be equally loaded, let's say. So I have a set of policies that drive the decision of where to put each container. There's a lot of exciting technology on this front. So we launched Galaxy on the Elastic Container Service, which is part of the AWS stack. We've also done a lot of work with Kubernetes, which is an open source project from Google that essentially distills what they learned from Borg and from running, I think, probably billions of containers on their infrastructure. Mesos is going in this direction. They have a technology called Marathon. All this stuff turns out to be really cool. Here's Kubernetes' take on it, for example. So we've got a lot of user containers. And the key piece is that how they're scheduled, the algorithm for figuring out where each container is going to run on your pool of actual compute infrastructure, is part of an orchestration layer rather than something you have to manually do. It looks just like how we used to manage the DOM manually, but now we have infrastructure that can do that for us. What does this have to do with connected clients? Well, let me show you one example of why this gets so tricky. So I mentioned before that when we want to do an update of an app, we actually have to update both the client half of the app and the server half of the app, and we have to do it in a coordinated way. So think about what it was like to update a Rails app. Let's say you're using Heroku as a turnkey platform as a service for updating your web app. Well, the way that works is you are going to deploy a bunch of new copies of version 2 of your app. If you want your app to stay up, those are going to be running side by side with version 1, right? So for a brief window of time, you're actually going to have multiple versions of your backend running in parallel. And as requests come in from clients during that window, they could get routed to either one. This is a hallmark of the stateless architecture. The whole idea is that you do your updates in such a way that a new version of the backend can handle a request from any version of, or from any client that's making it. And therefore, there's a window when a client could bounce between an old version, a new version, back to an old version. The theory is it doesn't matter. Once all of my new versions are up and running and they're healthy, then I can start tearing down the old versions, and I've done what looks like a zero downtime update. That strategy is colossally bad in a connected client app. Because remember, we can't be moving the WebSocket or my XHRs back and forth between different containers or different versions of the app. It turns out the way we do this, and I'm showing you again diagrams from how Galaxy works, is that we have to have a really careful understanding of the sequence of operations that happens as I go from v1 to v2. So here we go. We're running version 1 of the app. It's connected through a proxy to the backend, version 1 backend. Step 1 is I'm going to bring up version 2 backends in parallel. And our particular policy is we bring them all up at once. So we were running 4 copies of version 1. We're now going to run 4 copies of version 2. I haven't touched the WebSockets. The clients don't know this yet. They're all happily running on v1 still. Now, once the v2 is healthy, I can start in a rolling way to tear down the WebSockets of v1 clients. And I can inform the clients that there's actually a new version available, a version 2. And so what the client is going to do is it's going to request that new code bundle from the server. It's going to reroute its request into Galaxy as it essentially boots back up running the new version. And the proxy is going to ignore the stable session, right? Because remember, Galaxy's policy is we're going to route that client back to the same backend. But now it understands versions because it's keeping track of each client and which version of each client is running. And so instead, it'll establish a new stable session with an appropriate backend version. So there's a careful dance here between the old version containers, the new version containers, and the policy inside the proxy for when to start making the transition for each particular WebSocket. And I'm not even showing part of the detail here. So for example, as the new containers are spinning up, do we route incoming clients we've never seen before to old versions or new versions? So the reason that orchestration ends up mattering so much is that this gets a lot more complicated than the equivalent situation in the share-nothing web architecture, where it's just a matter of bringing up a bunch of processes, waiting for them to spin up, and then killing the old ones. I actually have to be a lot more careful about that policy for how many of each version I'm running and where they're running to maintain all of the clients having a smooth upgrade process, to maintain high availability, and zero downtime throughout the upgrade process. OK, so you roll that up together, and you have the makings of a modern application architecture. And there's more to it. We didn't talk about how do you run JavaScript in the device, and what does a native mobile container look like in 2015. There's a lot of cool stuff here. But you start to get the idea of what's involved, right? And this is what you see inside these modern apps that are available on iOS, Android, and the web being built in any reasonable amount of time. So we've got a reactive database query engine. We've got a way to sync the results of that reactive query up to the client. We've got a cache, right? We've built distributed caching. That is like classically the hardest thing to do in computer science. And we're asking web developers to do it in the course of building an app, which is completely nuts. We've got the speculative updates. So there has to be a way for us to even write data to the cache and then resolve that against what the server sent. We've got, of course, our reactive view layer, which everyone's on board with now. And on top of all that, finally, once we've integrated all those parts, written some of them ourselves, pieced a stack together from lots of different libraries and technologies, finally we get to write our actual components and our actual business logic. So the whole idea of Meteor is to centralize that investment in open source, because it turns out it's the same in every app. And once we recognize that JavaScript's the best language to architect these apps in, it becomes possible to make some decisions about the standard architecture that we should use. And some policies, very much like what Rails did for building web apps, so that we don't have to think about them every time we want to build a new app from scratch. Instead, we can just build the templates and the business logic. We don't have to ask ourselves, how are we going to translate ES 2015 to the right version of ES5 that runs in this particular mobile device, and then make sure we can push that code live into that mobile device using whichever new version of Cordova, blah, 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 right? None of that's creating value when you're building an app. That's just make work. So our goal is to centralize that. Here's another way to look at that. Probably the 2 most successful languages in the last 20 years. I know we're all excited about Rails and JavaScript, but like in terms of the number of apps that are built and the penetration into companies large and small, 2 languages have been incredibly successful. And the interesting thing about both .NET and Java is that they are consistent, complete platforms. So they don't just include a language, that's great, or a VM, that's great. They also include a whole ecosystem of standard libraries, of standard techniques, of partners, right? An ecosystem so that when you sit down to build an app in Java, you're not just deciding on a particular virtual machine that you're going to run. You're actually embracing a whole ecosystem from end to end on the stack. JavaScript doesn't have this. So it's really interesting. It's clearly the right language. It's the only one that runs everywhere and has incredible momentum. But it doesn't have the rest of that complete stack. That's what we're trying to do at Meteor. The idea is to bring together as open source a lot of the techniques I talked about, techniques that are, again, inside of the most sophisticated apps today, but make them accessible to all developers so that we can focus on building our apps instead of building the underlying technology and making these architectural decisions each time we sit down to build a new app. So thank you. I think there's time for a few questions. Yes? Mm-hmm.
So in that case, do you carry the state when you upgrade it to?
So the question is, when you do an update of a version, do you carry the state from one version to the other? It's an interesting question. So yes and no. The state is stored inside the server process. So in that sense, when you do a version update, you lose that state, right? The server no longer knows which data is being cached on the client. That means the client, when it restarts in the Meteor architecture, resubscribes to the data that it was already looking at. However, because it's an integrated stack from top to bottom, we can actually protect the user from seeing that effect. So for example, the cache didn't go anywhere on the client. So it's actually possible to do this in a way where the cache recognizes as the server comes back and the client reconnects and it listens to all that, we can avoid actually flashing the screen or causing big disconnects depending on the circumstance. So sometimes that's inevitable, but in a lot of cases where you've lost the state from a network connection, you can actually effectively for the user preserve the actual experience of being connected to the app, even though there was that disconnect.
Because you have cached data on the client, so you just push that to the server to prevent user to tell the server is being cached.
That's right. Yeah, and there's different techniques you can use to add more sophistication to that transition. And it's a good example of like, do you really want to be doing this inside each app? Like it's the same stuff. Right. But it's a different primitive. You won't find an answer to any of this in the web architecture, right? So we just think it's time for a different set of building blocks to build your app that way. Cool. Hang on, let me see if I should still be on the mic or just talk to you guys. There's a bunch of questions. Should I just keep chatting live or off stage? Yeah. Okay. Happy to stick around and answer questions. I'm just going to disconnect and I'll be right down here.